Hi.
Hi, how are you?
Good.
Yeah, what a great detector.
Yes.
Amazing. We can see almost everything now in this situation. Huh?
Yes, it's very nice. During the long shutdown too, lots of things will be moved apart so that we can see much more than we usually would.
So at the moment we don't see the beam pipe that carries proton, right? Mm-hmm. It should normally be through that blue circle and going through everything.
Yes.
You've removed it, I guess, for maintenance as well.
Yes, the beam pipe in this section has been removed for now, and also many other components have been moved. So actually, what you see here, the large muon wheel, is usually completely attached to this layer.
Yeah.
Such that we would actually be standing between these two large wheels that we are seeing over there.
Yeah, this is a very complex object. It looks like a big wheel, but I can see it's made in like slices.
So, this wheel is made out of several sections, and each of these sections consists of several layers.
Right.
And most of these sections are mostly identical, apart from minor geometric differences. But the different layers of this wheel have very different functionality. So, for example, you can see these tubes which contain a gas, and when the muons pass through, they ionize the gas. So there is a voltage between the outer layer and a tiny wire that is inside these tubes. And this voltage will mean that the ions that get created inside the gas will drift to the middle and to the outer side of the tube, and will give a small electrical pulse. And this electrical pulse we can see. So,
and that's a sign that the muon has passed.
Yes,
basically.
Exactly. So we have many of these tubes, and because we know the individual location of each and every one of these tubes, we will be able to detect where the muons came through. And this is only one of the many different types of technology that we're using here. And what you can see here, these large donut-type striped things, those are the toroid magnets.
This is a very specific thing of Atlas.
Yes, this is the very specific thing of Atlas. These are actually the magnets that inspired most of the design of Atlas.
Amazing.
Because people wanted to have a specific magnetic field for the outer layers of Atlas for the muon system. There are 8 of these. And so these are the 8 barrel toroids. There are also smaller versions of these that are inside this silver wheel that you can see at the end, which is also usually moved here around the beam pipe, and then put on top of the
what is it called? The silver piece. What is it called?
These are the end cap toroids.
Yes, okay. And as we go inside into the detector, more into the heart of it, what other components do we find after the octupoles, for instance, along the way?
As we proceed inwards, we also see other components that are intended for other types of particles. The next inner layer is the calorimeter. This is a very heavy, very dense piece of material that is intended to stop all of the particles and measure their energy as they are being stopped. So
calorimeter is a meter to measure the energy of the particles that come from the center going towards the outside.
Exactly.
Okay.
And so there's actually 2 different layers of calorimeter. The outermost layer is the hadronic calorimeter, and then the inner layer is the electromagnetic calorimeter.
Okay.
The electromagnetic calorimeter is intended to stop photons and electrons, whereas the hadronic calorimeter stops all hadrons, like, for example, protons.
Particles that contain quarks.
Yes, exactly.
And then more towards the very heart?
Yes, in the very heart is what we call the tracker. This is a piece of equipment that is intended to record the tracks of the particles as they go through. So we have a magnetic field that bends the particles according to the Lorentz force, and from the curvature of the particles, we can calculate the momentum that these particles have. So we have in our tracker we have several layers, most of them silicon. And as the particles pass through these silicon layers, what happens is essentially identical to what happens in the CCD chip of your digital camera, which is that the particles pass through a pixel, and that pixel produces an electromagnetic pulse, and this one we can record. And because we have many millions of these pixels right around the point where the collisions happens, we can see every particle that emerges from the collision. And because we have several layers of these, we can see individual hits, reconstruct a curve that is the track of the particle through these hits, and from this curve we can then calculate the momentum. And since after the tracker the particles hit the calorimeter, where they are stopped, we can also measure the energy. And with the energy and the momentum, we can calculate the identity of the particle.
That's just amazing. You compared Atlas to a CCD camera, to a digital camera, basically. But how many pictures do you take?
Well, I mean, we take about 40 million pictures per second.
Right, so this is the fastest camera on the planet.
Yes.
That's amazing. Okay, that's fabulous. Thank you very much, Karsten. I have to leave you because we are going to be live in a moment from up there, the very top floor of the Atlas detector. What a privilege,
amazing.
huh?
That's amazing.
Thank you very much. And welcome to CERN, welcome to the European Laboratory for Particle Physics and to the Atlas detector cavern 100 meters below ground. I left Karsten on the ground floor of this huge cavern. This is the largest volume detector ever built, to climb on top of it on the 6th floor. And I can tell you, it's very weird to look down to be on the 6th floor of something that is buried 100 meters below ground. This is one of the points where the LHC, the Large Hadron Collider, collides its beams normally 40 billion times per second. This is the very heart of the detector. And I can be here, of course, because the beam is off, the LHC is in maintenance, because the physicists from CERN and from the 4 collaborations around it, including the Atlas collaboration that is hosting me right now, they are preparing for the future, a bright future, a luminous future, as we will hear in a moment. We are live on Facebook. You can start posting your questions right now to the Atlas physicists, because they are going to answer all your questions, hopefully as many as possible. And I'm going to welcome the first of our guests here. Actually, I am your guest, Manuela Winkter, Deputy Spokesperson for the Atlas collaboration. Thank you for having us here.
Hello. Thank you very much for inviting me here.
So this is really an impressive place. I'm extremely excited to be right on top of the largest volume detector. How big is Atlas?
So Atlas is as big as a small cathedral. It's about 40 meters long and 20 meters high. And it's 7,000 tons. And if you're wondering what 7,000 tons weighs like, that's about as much as the Eiffel Tower weighs. So we're almost like standing on top of the Eiffel Tower here.
And you built it all here in this underground cavern a few years ago, before the LHC started its program, right?
That's right.
You meaning how many people in your collaboration?
Well, at the moment, Atlas has more than 5,000 people collaborating. Out of those 5,000 people, there are about 1,000 PhD students. There are scientists. And because of all the work that's happening over the next couple of years, there are actually many engineers and technicians that are helping us to succeed in the upgrade of Atlas.
You are Canadian, right?
I am. I'm from Carleton University in Ottawa in Canada.
And how many other countries are participating in this incredible collaboration?
So there are 38 countries that are officially participating in Atlas. However, if you look at the nationality of all the people who are in Atlas, it's actually closer to about 100 different countries. So it's a really very diverse collaboration.
Not just European, of course, as you yourself demonstrate.
From everywhere, from Europe, from North, South America, from Africa, from Asia. They're coming from everywhere except maybe Antarctica.
Yes, well, very soon maybe.
That would be great.
So, as I said before, you are preparing for a bright future. The luminosity program of the LHC, the high luminosity program.
Yes, indeed.
And I'm welcoming here with us one of your 5,000 collaborators, Carl William
from the University of Liverpool in the UK.
Okay, so Carl, you are one of the 6,000 physicists, and I want to ask you first, what does luminosity mean for a physicist?
So luminosity is a measure of how many collisions we have inside Atlas. So really, the more luminosity we have, the more collisions we have, and therefore the more events we have. So we can have 10 times more events with the high luminosity LHC, events like these. So we have very rare processes that we can now see that we couldn't before, but they're very rare. So we need to dig them out from these very complicated experiments. So 10 times luminosity means 10 times more events, but the detector is 10 times busier.
So even if you are not getting events, which is basically what the collisions give you, in the center of your detector. You're busy simulating them. Why?
So because this is such a complicated event, we need to simulate them in order that we can train, in order that we can learn to separate the events we're interested in from the large amount of background. So because it's so much more complicated and so much more busy, as you saw, we need really complicated analysis techniques using big data to really separate them. And we need to train those so we're ready when we start taking data.
While some physicists of the collaboration are training with events, we're going to go on the physics of it in a moment. Most people at CERN, especially around the LHC machine, are really building hard stuff. Like here in point one, where we are on the surface, they just completed another shaft like this one right above our head, 80 meters deep shaft. They're starting to dig another cavern similar to this, and many surface building to host all the technology that the LHC needs to give you 10 times more events than the previous program. In this time, members of the Atlas collaboration are also busy getting the detector ready to take all these many more collisions. What would happen? What would happen if you had these collisions right now? Would you be able to read them?
No, actually not very well. So what we need to do is we need to improve our own technology. The LHC is becoming so much better at giving us this data. As you saw in the picture, it's very dense collision data. And so Atlas needs to keep up. So what do you do when you need to take a better picture? You need a better camera. And that's essentially what Atlas is, actually. It's just a very sophisticated camera. And that's why we're improving the detectors that are able to see these particles.
So, of course, we cannot go through all the changes, new technologies that you are devising. But what are main operations that have been done and are being planned so far for making this detector capable of reading 10 times more collisions than before?
So right now, our most ambitious project is well underway, and this is it's a new detector called the new small wheel.
Small? How small? Because
small,
here small is very relative,
it's
right?
It's only about 9 meters high, so that's the small.
Yeah.
So the new small wheel is actually under construction right now above head, but you can actually see what it sort of will look like, because right now, underground, we can see the old small wheel. And it's a detection device that whose job is to see muons. And muons are just basically heavy electrons.
Why are they important?
Well, actually, a lot of the interesting signatures that Carl was talking about actually produce these particles.
Like these ones. Do I have them on my T-shirt?
Yes, perhaps you have the muons on your T-shirt. And so if we want to be able to see, the thing is that a lot of things look like muons, but they're imposters. They're not really muons. So what we need are better detectors to be able to tell the difference between what are real muons and what are things faking muons.
How heavy is that small wheel?
It's actually not so heavy. It's probably a few, maybe 1 or 2 tons, a few tons.
Still, 1 or 2 tons to be moved out of a shaft 100 meters below ground. This is quite something.
Yes, but it's actually one of the lighter components that we have.
So
and it's a small wheel.
Easy.
And we actually have the bigger version of the big wheel just behind it. So you can really see what a big wheel is. And a big wheel is more like 20 meters high.
Crazy. So I also know that you're installing some new chambers. 16 of them have already been installed. They're called small monitor drift tubes.
That's right.
What are they? And what do you need them for?
So these are also to see muons. So this new small wheel, if you look at the Atlas detector, it sort of looks like a cylinder, and the new small wheel come in the ends of it. Now, that's great. However, just between the new small wheel and the rest of the detector, there are places there that we don't have very good coverage for identifying muons. And so what we want to do is we want to replace them so that they're more performant for when the high luminosity LHC gives us all these particles.
You also have new resistive plate chambers.
Yes, that's right. So this detector, which you said reads several million times per second, actually most of the time is not actually doing much. What we need to do is we need to wake it up every 25 nanoseconds and say, hey, there's something interesting to take a picture of. And that's what these RPCs
Every 25 nanoseconds.
Every
okay.
20, so
it's a very fast camera.
It's very fast. So, the light travels really fast, but in 25 nanosecond, light travels only 7 meters. That's how fast.
So you're much larger than that.
Yes.
Longer and bigger than that. Okay, then you're enhancing, not just new things, new technologies. You are just making it stronger, more powerful.
That's right.
One example.
Well, so actually most of the detector is going to be staying with us for another 20 years. We have very robust detectors. One of them is a calorimeter, so that's an object that measures the energy of the particles. The instrumentation itself is great. However, just like a car that's been running for a while, because when Atlas runs, we run 24/7, 7 days a week, 10 months a year. And every once in a while, you just have to stop and just repair things.
Right.
And
It's
these
so big, but it's extremely sophisticated. And
That's right.
some components are really delicate.
Some components delicate, and actually a lot of the things in Atlas have been down here for about 15 years now.
Right.
And so it's just time to actually go and replace some of the things and just repair.
This is all super spectacular. So I remind you that we are live on Facebook, and you can send your questions to Manuela, Deputy Spokesperson of the Atlas Collaboration, and to Carl William, exotic physics expert, but I guess you can answer all the possible questions on the physics.
I hope so.
And now, so we've seen this enormous improvement, some of them, because there are many more happening, and that will happen for the next few months until 2020. We've seen it's because you want to be able to read more collisions. But what for? What is the physics challenges that you can be ready to grasp with this high luminosity program of the Large Hadron Collider?
So so people will remember that we discovered the Higgs boson in 2012.
Yeah, not very soon is going to be the anniversary of the Higgs
Yeah,
boson
it's
discovered
gonna
by
be
you and your
anniversary.
friends from CMS Collaboration on the opposite side of the Large Hadron Collider ring.
Exactly. And so we haven't seen anything else new yet, but we have strong arguments that there should be something else new in the region of the Higgs boson. And we don't, so in the region of the Higgs boson. And we want to be able to find that, but it might be that nature hasn't been very kind to us. Maybe it's not very easy to find, but we like a challenge. So we need to be able to identify these events. So this means more collisions, so more events.
Yes.
To be able to see things that are rarer, and also more sensitive detectors, as Manuela was saying, more pixels, a more sensitive camera, to be able to measure things much more precisely and look at unusual signatures that we couldn't do before.
Yes, but for instance, name one new particle that you would like to dig out from these very complex events that the high luminosity LHC is going to provide.
So I think the obvious example is dark matter. We know that dark matter, some things we cannot see, make up around 25% of our universe. We know this from looking at the galaxies in the sky and seeing how they move. But we don't know what is responsible for this dark matter. Is there a particle? And that's one of the things that we're really trying to find.
This is a big challenge for cosmologists, theoretical physicists, astrophysicists who are looking with telescopes, trying to see something that is invisible. And in the LHC, the procedure to discover dark matter is a bit different because you're trying to see how it is born from the collisions. You basically recreate the universe in miniature.
Yeah, so Atlas looks at how the universe was less than a billionth of a second after the Big Bang, trying to recreate those conditions. So we, unlike looking at astronomers that look at the sky, we can try to recreate dark matter in the laboratory and really then study it and see what it's made of, what causes dark matter. So we look for things that kind of escape our detector, and we look at these events we have and try to infer that there might have been some dark matter there.
This would be sure a Nobel Prize, Manuela.
I think it would definitely be a Nobel Prize.
And what is your favorite new particle or new phenomenon that you might be able to find with the high luminosity?
Well, there's a category of particles called supersymmetry. And supersymmetry is actually a very beautiful theory. It would complement very well what we actually know about the universe right now. It would almost be like completing the picture of the universe. And it's actually particles that we've been looking for since the very start of the LHC. So far, we have not been successful at seeing it, but I haven't given up hope yet.
You will apologize if I use
Yeah.
my phone, but this is for a good reason.
Okay.
Because my colleagues in the social media team of CERN are flooding my phone with questions for
Okay,
you
sure.
guys. So I'll read the question and then you raise your hand
Okay.
who wants to answer. So this is from Rodrigo. Thank you, Rodrigo, for being the first to start this chat. So why does the machine has to be underground? Why does Atlas and the whole LHC have to be underground? Manuela, what's your answer?
Well, so the LHC is something that's 27 kilometers long. And so if we were above ground, we would need basically to have a racetrack that is 27 kilometers long, and that actually takes up a lot of land. And this is Europe, this is France and Switzerland, and so land is actually very expensive.
And also people live here. We
And
cannot
people live here.
expropriate.
We don't want to kick people out, and so instead we just dug underground and we built the accelerator underground.
Great. Before Rodrigo, actually Alex asked, is CERN expected to prove experimentally the existence of supersymmetric particles in the next years, or are those particles not important anymore? Should we change the known physics of supersymmetric particle? What's your take, Carl?
So yes, we're still looking for supersymmetry. We've ruled out a lot of phase space, but there's still a lot of places where supersymmetry could be hiding from us, so we're still looking for it. It's still, as Manuela was saying, a very well motivated theory, so we're still looking for supersymmetry, but it's also, we're looking for all sorts of new things. Dark matter, looking at antimatter, looking at all these big questions. So it's equally important, I would say.
So we can say that Susie, as supersymmetry is dubbed by the theorist, is alive. And John Ellis will be very happy, I think.
He was happy, yes.
Yeah. So Mirvat asked, I would like to know about calorimeter. What's its function, please?
Yes, a calorimeter is a device that measures the energy. So what happens if we have a beautiful calorimeter here that is made from steel, and it's also made from polystyrene, basically styrofoam cups. And what happens when a particle goes through, it hits the steel, it stops in the steel, it just warms up the steel, it just deposits its energy in the calorimeter. And then the styrofoam, which is basically a type of plastic, is able to pick up that light, collect the light, and measure how much light came from that particle. And from that can infer what was the energy of that particle.
So it's a calorimeter. It's like
Calor.
the Latin word
Calor,
says, calor,
heat. That's right. It's a
energy, which can be also compared
That's
to
right.
energy.
It's an object that measures the heat or the energy.
Right, perfect. Jamel, what experiments are you conducting today? What are its objectives? I guess today, when we have no beam, the experimental program is still going on. You're very busy on that. What are you doing?
Yeah, we're very busy on that. So we've taken data now for about 5 years, and we haven't had a shutdown. So we've been busy taking this data, and we've accumulated lots of data, but we haven't had full time to analyze it. So there's many physicists working on analyzing it, making very, very precise measurements of particles, and searching. So what I lead is searching for new physics. So there's many people doing that, and there's lots of data still to be analyzed, and we still hope we might find something in this, some tantalizing hints that we can then look for further at the high luminosity LHC.
And let me remind that very soon in the summer you are having the physics conference for all the LHC experiments. And so maybe Atlas is going to announce some new publications, new...
Who knows?
Who knows? Who knows? So keep following what these people are doing. They have a fantastic outreach website as well, where they share everything they do with the entire world. So, Rodrigo again, can we use dark matter in any technology in the future? Any ideas?
So it's hard to tell ahead of time, but there's an anecdote that I really like, is when lasers were first discovered, people had no real applications for them. They thought it was a cool physics phenomena, don't know what it's used for, but hey, we discovered, we know how it works. And now it's hard to imagine a day when you don't actually use a laser in some way, whether you go grocery shopping or you use it in equipment. So it's hard to tell ahead of time, but in the future, what we discover now could very well become something that you use day to day.
That's always been the case in
particle physics. It's always been the case like that.
Yeah, and for instance, I think for sure the detectors you're developing to see what is really invisible by definition, they're going to be very, very powerful in many fields,
even today.
Even today. For
That's
instance, your current detectors are used, the technology developed for them is used in hospitals, both for therapy and for diagnosis.
Yes.
And in
Most
computing, and applications come every day, basically.
Most major hospitals have their own accelerators. They have their own particle detection devices, smaller versions of Atlas. So it certainly has trickled down into all areas of society.
Lisa is asking, what is with the upgrade, what is the increase in luminosity?
So with the upgrade, we'll increase the luminosity by a factor of 10. So we'll have 10 times more events. And that may not sound like so much, but it's really important because many things, if they're quite rare, then we might not have actually produced them yet. We need more collisions to actually produce some of them. If we don't produce them, we can't find them. So we need that increase in luminosity so that we can produce these events so we have a chance of trying to find them.
Very good. Vaibhav, is there any experiment of particle collisions in anti-gravity and microgravity in ATLAS?
Not in ATLAS per se, but actually at CERN there are experiments that do work. They work on gravity, and they work on gravity of antiparticles. Yes.
Yeah, we did one live not long ago from the antimatter factory.
That's right.
You can watch the recording, and we were interviewing physicists working exactly on that. G bar, for instance, is one of the experiments. Alpha G is another experiment. They are exactly getting ready. They've already done some measurements, but the real physics will start with the new run of the LHC in 2021.
Yes, a lot of experiments are on hold right now, doing repairs just like us and waiting for the LHC to wake up.
Matthew, also somebody interested in antimatter. I visited CERN a few years back and gained an interest in antimatter. At the time, anti-hydrogen atoms were possible, anti-helium was not. Has human understanding of science now moved forward from this point? Meaning, have we made anti-helium?
I don't know, actually. Have we made anti-helium?
I don't think
so.
I don't think
so.
I think
they've made a lot. They've made anti-hydrogen. They've made quite a bit of anti-hydrogen by now, but I don't think it's.
There has been a lot of progress with anti-hydrogen, not just making one atom or a few bunch of atoms, but they make millions of them, and they manage to trap them long enough to be able to study if anti-gravity exists. So this is already enormous progress, and it's actually enough to study phenomena like anti-gravity or how antimatter behaves, the anti-wall, whether it exists or not. So why take the pain of making anti-helium if you can make anti-hydrogen, trap it and study the same phenomena? Okay, one more question here. A second. So Montserrat is asking, what about gravitons? Are you looking for gravitons in your experiments?
Yes, so we're looking for gravitons. So gravitons are these hypothesized particle that could explain gravity. At the moment, we don't know what is responsible for gravity. If there's a particle, many other forces, they have particles associated with them. So yes, it's actually something we search for in the group that I lead, is we look for different decays. So these gravitons will be very short-lived, very unstable. They decay. And then we look for the things that they decay to, and we're looking in many different channels, and these searches are ongoing, and hopefully we'll have maybe even some new results for this conference in the summer that you mentioned.
Ah, wow. This is a little hint to be followed up. That's great. So, one more question now on the detector itself. How did you decide what were the best materials to use during the construction?
So actually, there are quite a few things we have to look into. First of all, it's very crowded down there, so there's not a whole lot of space. So whatever material we use, we have to be able to make it fairly compact. The other thing is the beam runs quite regularly, which means that there's actually some radiation when the beam is on. So we need to have materials that are radiation resistant, that are not going to dissolve or be damaged by the radiation. So those are two of the important criteria that we consider.
There are lots of requirements.
Lots of requirements, exactly, yes.
Yeah.
You have to look at what the purpose of that detector is, and you have to choose the material that does the best job for that.
And that's why these detectors are really their own prototypes, basically. They're not something you can buy anywhere.
No.
It's the 6,000 people in ATLAS, their universities, that put together
That's
the technologies and the materials, sometimes with the help of industry for the huge components,
That's
for
right.
instance.
And in fact, that's how we do our partnerships with industry. What we will do in our home institutes, in our universities, is we'll often do small prototypes just to test out the physics principles behind it. And once we're pretty sure that it's going to work on a large scale, then sometimes we'll invite industry to help us to produce the large-scale detectors, because we just don't have the equipment to build things that are really this big.
And this is a learning process also for
Yes.
industry. This is great. One more question on supersymmetry. Why super partners or something that can support SUSY haven't shown up yet? Why?
So yeah, we might have imagined they would show up yet, but it may be that they are very difficult to see. It may be that they decay into things that are very rare, or that they decay into things that are very low energy. And things that are low energy, we find it very difficult to see. Or it might be that it decays into things or it has a lifetime that's longer. So we're very good at detecting things that come right at the interaction point, that decay straight away.
Yeah.
But if things travel some distance before they decay, The detector's not so good at doing that. This is one of the challenges and also something that the high luminosity LHC, the new detector there, the upgraded detector, will help us to observe. So it might be that it's something like this that we've not yet been able to see.
And I wish you the best of luck with that. So Andy, on average, how much data do you generate during a given experiment? So as Manuela said, experiment here means 10 months in a row, 24 hours a day and 7 days a week. So experiment is a special concept. So how much data do you generate?
So we generate, we create here in our laboratory billions of events. And so to store this information, it usually requires us to disk space, which is petabytes. So gigabytes, terabytes, petabytes. So that's the scale of the data we have to take.
Petabytes of data. Some comparisons say it's a pile of DVD from the Earth to the top of the Mont Blanc.
That's right. That's right.
So this is how much the LHC generates, and this is the reason why we had to build the worldwide LHC computing grid, something that puts together the computing power and the storage power of many computing centers around the planet, some 200 of them that put together. Otherwise, it wouldn't be possible to process all this data and to store all this data. There's one strange question from David, but every question is welcome. When will we try to split atoms again? Splitting the atom, I guess it means nuclear fission, which we don't do.
Yes, that's right. We don't. So Atlas does not do that because Atlas doesn't actually use atoms. Atlas uses protons, so that's the substructure of atoms.
Atoms are too big.
Atoms are too big for us, but it's also not the focus of our research here. I'm sure that there are other facilities where they focus on in nuclear physics on working with atoms, but this is not what we work on here.
Okay, so one more question. Can we visit Atlas? What are the restrictions?
So actually, this is a good time to visit Atlas because during the long shutdown, the LHC is not running. But it's actually a very busy place right now because of all the construction that we need to do. So it's only small groups of people at a time that we can take down. However, there is the CERN Open Days. So this is September 14th and 15th, right here at CERN. And we will be taking as many people down as we can over that 48-hour period.
CERN can be visited all the time. As you said, this is the best time. The only trick is book your visit in advance.
Yes.
You can see how complex it is to come down these caverns. We want to take as many people as possible here underground, but you have to book in advance. And including on open days, if you want to go up underground, you have to register, and the website is home.cern or opendays.cern, and you find all the information, including the procedure to register. One more question from TC. Will these experiments help to emerge new subatomic particles? This is exactly what we wish they do.
We hope so. We hope very much that they will. Like I say, there are things we don't understand in nature. There maybe there's a deeper theory than the one we have now that predicts new particles, and without them, you know, there are really things we can't explain. Like I mentioned, dark matter, we don't know what it is. Our current theory wouldn't predict any particles for it. So we believe there is a more complete theory that predicts new subatomic particles, like maybe dark matter. So yes, we very much hope so. We just need to keep trying to find them.
One more physics question from Anas. Could you test quantum gravity soon, anytime soon? Quantum gravity.
I think that this is not something really in the focus of Atlas to test quantum gravity. There are other experiments working on this, but this is not something Atlas is really set up to do.
Maybe it's something for the gravitational wave experiments.
Yes, much more the gravitational wave experiments.
Yeah. Okay. Yeah, about the gravitational waves experiment. Now that we know that there are gravity waves, does this provide an insight? And in general, do new breakthroughs in astrophysics help particle physics?
Of course, we don't work in isolation. Science is a big field, it's multidisciplinary, so things we learn from astronomy help particle physics and vice versa. So we learnt about the fact that there's missing matter in the universe from astronomical measurements of galaxies, and now we're looking for the particles responsible for this. With the gravitational waves, you know, we know that gravity behaves like a wave and like a particle, and now we're looking to try to see the graviton. Can we find a particle responsible for gravity? And the more information we know about how gravity behaves on a big scale, the more we can pin down what it might look like as a particle, and this helps us pinpoint where to search.
Okay, so one more question. When did you start the construction of Atlas, and how long do you expect is it going to last?
So the very first thoughts about Atlas actually happened in around the 1980s, mid-1980s, late 1980s. So it's been a long time. The construction of Atlas, the first components were happening perhaps in the late 90s. And the first components to come down here in the cavern was in the early 2000s, 2003, 2004. Construction went on until about 2008, which is when we started to take the very first LHC beams.
And how much longer do you expect this detector to be exploited?
Actually, long beyond my retirement. So at the moment, there's a future for Atlas until about 2035. So there's a lot of opportunities for people to come and start their careers here and spend the next 20 years working on
So even
Atlas.
young students in high schools
Yes.
can expect to do their PhD thesis in the Atlas detector.
That's right. You could come here, do your PhD thesis, and eventually be some of the people who actually lead the experiment.
And you could
to
start
its
even
success.
earlier, because at the moment there are summer students at CERN, and you
That's
could even
right.
do a summer studentship here.
That's right. Every year, CERN welcomes several hundred students from undergraduate university level, and they come and do a program here of about 2 months where they take courses, and they also work on the experiments, doing some physics measurements.
I have two more questions, and I would say let's take these two, and then we close. So from Lynn, how do physicists remove the protons from atoms for collisions?
Sure. So the beginnings of the LHC is actually quite humble. A proton is just, it's mostly just hydrogen. If you think about it from high school physics, hydrogen is a proton and an electron. And so the beginnings of the LHC is just a bottle about this big. That is a bottle of hydrogen. They strip the electrons from it, and then you have protons.
How do you strip the electrons? Because that's what was the question about. How do you do that?
Okay, so the electrons have a negative charge, and the protons have a positive charge. So you're able to just strip the electrons off, just taking advantage of the fact that they're charged particles.
And then Sergio, thank you for your question. He says, but you're also using heavy ions. So what are the main limitations when you use heavy ions in the collisions?
So with heavy ions, we obviously have lots. So normally we collide just one proton. With heavy ions, we have nuclei with lots and lots of protons. So the events have even more particles in them. So the detector becomes very full. It's all, it's even more than we might see in this high luminosity LHC for Atlas. So Atlas does some physics with heavy ions, but there's also a dedicated experiment, Alice, that looks at heavy ions. So these are just much, much busier events. They're much, much more dense. They have many more particles, and taking all that data is just much more complicated.
So Alice, we did a live from the Alice detector in March. You can watch it again, because every one of our lives, including this one, stays on CERN's Facebook page and YouTube, and you can watch it again and again. And I would like to close with two main messages. So this experiment is really for everyone. It's for you, young, promising future physicists. If you like math and physics and you are still studying at high school, you can still do your thesis here. You can still come here as a summer student. And it's also for everyone, because CERN welcomes visit, and of course the Atlas detector welcomes visitors, especially this year, every day, but especially on our open days on the 14th and 15th of September. Register to take part and to visit underground.
Come join us.
Thank you, Carl. Thank you, Manuela. Thank you, Atlas. And bye, everyone.
Bye.